Greetings. Hello. Hi. Welcome. So let's talk about integration, specifically the following integration. All right. Let's talk about the integration of tan to the fourth power. The limits are pi over 4 and my upper limits are pi over 3. So we're given to integrate the following. 12 tan the fourth power of x dx. And the question is, show that this whole entire integral is equals to pi, this is pi, plus 8. So yes, that's the question. Show that the integration of 12 tan to the power 4x is equivalent to pi plus 8. And we know that this is a definite integral because it has defined limits with the upper and the lower limit. Alright, enough about that stuff. Let's go ahead and prove this. So start with green. Okay, starting off, we'll factor out a 2 from the integral. We'll take the 2 out, put it outside the integral sign because it's a constant. Pi over 4, pi over 3, I'm just rewriting that as it was initially. I'm not worried about the boundary at the moment. What we are worried about is this term inside the integral sign. So let's break it down. Okay, let me just rewrite that guy as he is. Then all this becomes, still have our limits. Then let's rewrite that as a product of tan squared. So we can rewrite that as tan squared x multiplied by tan squared x dx. The reason why we can do this, it's because of, well, from algebra, we know that if we have x to the power 2 multiplied by x to the power 2, the bases are the same, therefore we just write the base as it is and add the powers 2 plus 2, so that gives us x to the power 4. So we can break this one down or rewrite x to the power 4 back into, well, as a product of its prime factors, which is x squared and x squared. That's what we just did here. We applied this basic rule to this guy. Alright, cool. Right, just erasing that. So now let's move. Cool. So the next step is to introduce an identity, and we'll use the following identity. I'm sure you know the following already. I'm sure we are all aware of the following identity. 1 is equals to sine squared x plus cos squared x. This is like the basic identity which everyone knows. We need to, but what we are looking for is tan squared. So what happens if we divide this sine squared by cos squared x. Well, we already know that sine x over cos x is the same thing as tan x. I'm sorry about my writing there. Already know. Okay, I'm out of page here. This is the same thing as tan x. Okay, cool. So we'll just divide everywhere by cos squared x. When we do that, 1 over cos squared x, we know that 1 over cos is sec, but right here we have 1 over cos squared, so this will be sec squared. Sec squared x is equal to, this becomes tan squared x plus cos over cos, they are all squared, this is just 1. So we are interested in having tan. From here we can make tan subject of the formula. Tan squared x is equal to sec squared x minus 1. So this is our identity, and we can use this, substitute in one of these guys, so we can replace one of the tan with this identity here, and replace this tan here with that identity. Okay, so this whole thing becomes we still have our 12, we still have our limits, we haven't done anything to our limits, we'll still have this guy, and the following will change, sec squared x minus 1, and we'll still have our dx. So right here we just expand the brackets, we just multiply through by tan squared x. So that becomes, we haven't touched these guys, so we write them as they are. That becomes tan squared x. Just correct that. Becomes tan squared x into sec squared x minus tan squared x, everything inside brackets, dx. Alright. Okay, this is looking good so far. So now we just distribute the integral sign as well as the 12, the constant 12. Just distribute those guys. Oh boy, so much space here. But okay, we'll use, I did not plan my work nicely, but it's fine, this will do. Okay, let me change the color, so 12, our limit is still the same, tan squared x sec squared x dx minus 12. I'm just distributing the constant 12 and the integral sign and the limits between the two terms inside here. That's mathematically allowed. We're not breaking any rules. Tan squared x dx. Alright. Now we have two terms which we can integrate separately. Let's focus on this one. What is the integral of tan squared x? We don't know. Well, not that we don't know. Let's find out. It's not so easy to integrate at the moment. So what we can do is replace tan squared x with an identity of which the integral we do know. Therefore, that will simplify our work. But wait a minute, we already know that tan squared x is actually, it can be replaced by sec squared x. We can replace tan squared x with this integral, with this identity, which is sec squared x minus 1. So with that knowledge, we can just do that here. That knowledge, we can just say, okay, minus 12 integral pi over 4 pi over 3. Note, we haven't done anything yet with the integral. We haven't integrated yet. All we are doing is just simplifying this guy into an expression that we can easily integrate so that we can carry out our integration. Okay, now we have this guy. We can distribute again the integral sign and the limit and the constant. So this will become 12 integral pi over 4 pi over 3 sec squared x dx minus, and the minus becomes plus 12 integral limits dx. Okay, so now I'm just focusing on these guys, on the second term. So the second term is broken down into two terms again. So alright, let's see. Do we have any idea what the integral of sec squared x is? Sec squared x, what is the integral of that guy? Well, yes, we do know the integral of sec squared x, that is tan x. And this is why we know that integration is the inverse of differentiation. Let's say we're given a function, let's say we're given y is equals to tan x, and then someone asks you, or your friend asks you to differentiate tan x. You just go ahead and do the following. dy dx is equal to sec squared x. So sec squared x is the differential answer to tan x. Cool. So your friend says, okay, fine. Now I want you to integrate tan x. But we know that integration is the inverse of differentiation. So you can just go ahead and integrate this to go back to tan x. And how will you go about integrating sec squared x in this scenario? Well, you go ahead and just say, okay, I want to find what my y value is. So you rewrite this guy as dy is equals to sec squared x dx. So we are integrating in terms of x. Alright, so integral of y. So integral of y, I would say maybe from 0 to y. Those are our integral limits, and the integral of sec would be from 0 also and to x. So when we integrate this, dy will become y, 0 sec y, and the integral of sec squared x is exactly the value we began with, which is the function we derived to get sec squared x. I'm hoping this is sort of making sense. If it doesn't make sense, I will just follow along with the video. It will eventually make sense. So the integral of sec squared x is tan squared, tan x, and our limits from 0 to x. So what we do, we substitute our limits. Upper limit minus lower limit is equal to tan x is our upper limit minus tan of 0. Tan of 0, what is that? Tan of 0 is 0. So there you have it. There you have it. The integral of sec squared x is actually tan x. So all I was doing here is I was just proving to you that the integral of sec squared x is actually tan x. You don't have to do this proving in the exam. All you can do is, you already know your integral of sec squared x. All you do is to answer this question. You just write down your answer. Integral of sec squared x is tan x. Then put our limits there from pi over 4, pi over 3. We haven't done anything with our limits. We haven't used them yet. And what is the integral of 1? There's an imaginary 1 here, 1 dx. Well, if we integrate the constant, becomes a variable. If we integrate 1 or 2 or 12, you just get the variable. So this changes to plus x, and well, these are our limits of integration. We haven't done anything with them, so we just bring them down, carry them along as they are. Okay, all right. There's no need to put plus c because we're given our upper and lower limits. Okay, cool. So this guy is done. The second term is sorted. We're done here. Now let's look at this one. Let's look at this term. Okay, looking at this term, what do we know? Well, we know that the derivative of tan x, is, if we derive tan x, like u prime of tan x, will give us sec squared x. So we can using this fact,